This one is for him.
Okay, welcome to my talk. You will see not my name on it. This is Mr. Axel Tierling prepared this presentation for you, but unfortunately, shortly before we left the country, he had a positive test for COVID. So I'm going to fill in for him. So maybe he would be the better expert on this, but nonetheless, I will give my best to fill in every question. So the topic that we have prepared for you today is our recent work about object detection under image noise, and specifically for agricultural use cases. So I will be talking about the perception systems that are mounted on agricultural devices in practice and what problems they face also. And spoiler alert, the problem that they're most likely to face are noise, unwanted noise values in the images they detect. And so this will be our motivation to talk about noise models. What kind of noises can we mathematically model and expect in such images? And we will talk also about denoising techniques. So what can we do, or how can we filter to remove some of this unwanted signal in our data? We will evaluate this whole thing on an object detection task, which is a classical task for agriculture. We saw it already, for example, in the presentation preceding mine, in the detection of the weeds fruits, for example. But we also use this for obstacle detection and many other things. So this is a very, very fundamental concept in automation of agriculture also. And then finally, we will conclude with the experiments and results. So yeah, as I already told you, yeah, the machines that we have these days, specifically for precision agriculture, they are equipped with a lot of sensors. But due to their mechanical construction, this yeah, the sensors that are mounted there, they face specific challenges. Because if you see, this is like a harvester machine from Germany by the company Fendt. It is probably as big as this room from here to there, and as tall as 3 or 4 people. And basically, we run into problems of cabling all those sensors together, because we get very long cable lengths, especially for cameras, which a lot of them function via USB still. We would need repeaters. This is often not feasible and leads to many hardware issues down the line. We already faced that at smaller machines. If you saw Professor Burns' presentation, for example, our Unimog, which is an off-road truck, which is maybe 1/3 of the size of this. And already with that, we face lots of problems in the hardware of sensor mounts. So what is done is using wireless transmission to do this. We often use the cameras that are available on the market for the agricultural use case, often even use analog wireless transmission, because it's just easier to realize in this hardware system that we have there. But this transmission, as it is right there, it leads to a lot of noise that is introduced due to interference, due to whatever reasons. And also, of course, in this use case, we also have a lot of environmental noise factors that come with it. For example, think about the dust that is produced while such a machine is on the field. Yeah, so as I already mentioned, there are very fundamental things that are have to be done in agriculture. This is for one instance surveillance stuff. So we want to extract some key performance indicators from our crops. This would be food yield, for example, the state of the soil and the plant health, because those are all those are things that can help the farmer to counteract and make different decisions and optimize his crop yield. And on the other hand, we also have automation. This is specifically a very important use case in Germany, because a lot the job of, or the career as a farmer isn't a very attractive one in Germany. There's less and less people who want to pursue this career path. So we have no other choice basically than to try to solve these problems via automation. And for this, today, for our talk here, we will specifically focus more or less on this obstacle person detection use case. But this is what I was talking about. It's applicable to basically every aspect of this because it tackles a fundamental issue. So yeah, let's get to the noise models. Here we see some images that we have taken from a person detection use case for safety measures, basically from top-down view. And those we chose this because those were collected via an analog camera. So similarly than to what we expect on big agricultural machines. And yeah, we have simulated, or there's in literature, there's a lot of noise models available, so mathematical formulations with which we can introduce such noise. And this is for, on the one hand, well, of course, you don't see it that well on the projection because it's just noise. There are some very slight differences, but this Gaussian noise, I think a lot of people are familiar with this, because this is a very, very fundamental type of noise arising from the Gaussian distribution. Salt and pepper noise, this is more binary, so this is like black or white pixels that are introduced somewhere. And this is also relevant because this mimics the failure characteristics of image sensors, because you can have dead pixels or saturated pixels, for example. So this is something that is introduced there. And I don't want to talk too much about the other noises because they're noise. The difference is just in the mathematical formulation of how we introduce them. There are very many of those. Some are also not only just pixel based, but maybe affect the whole image, like the brightness noise or bloom effects. We also consider those as noise sources. You can imagine those, for example, if you use your agricultural machine and suddenly you look into the sun, right? So this introduces these bloom effects, for example. It's also a very important thing that happens, phenomenon that happens. So yeah, how can we tackle those things? There are many things available to us from classical methods. We try to use as many classical methods in combination with deep learning methodologies here. So for example, we have the mean filter, the median filter, Gaussian blur, and those are the more common ones with a simple formulation. And then we have tried also some others, like the bilateral filter, which is a guided filter, and a wavelet filter, which is similar. Wavelets are a decomposition into basis functions, like a Fourier transformation, if you know that, if you're familiar with that, but just with a little bit more complex basis functions. So instead of just having sine and cosine waves as your base function of your base of the signal, instead you have arbitrary and more complex waveforms that your image or signal can be decomposed into. And for our experiments, we basically have trained or looked at 3 modalities. We have introduced a low, medium, and a high noise amounts. And we have looked into what methodology is best, or first of all, we have looked into how this affects our prediction, how much worse is it under those conditions, and then we have evaluated how much better those filtering techniques make it. And to evaluate it, as I already mentioned, we have used this very common and fundamental use case of object detection, particularly a faster RCNN algorithm, which is maybe not state of the art anymore, but very broadly used in the field. Basically, the practitioner's choice maybe of object detection algorithm. It was coupled with this ResNet 101 backend, also very common in the literature and in practice, because we wanted to basically look at the usual use case. And yeah, and then let's get to the how did we evaluate this? And I think this is where this becomes interesting, because on the one hand, we looked at those normal indicators that we usually have, which is the mean average precision. This is like the most common evaluation metric for object detection, and was introduced on many of those data sets that we commonly have, like COCO data sets, for example. And to evaluate the performance of the filters, we have used a peak signal to noise ratio. So how much of the signal basically contains actual data and how much is noise. And then the third point, here we wanted to look at this whole thing from a more formal, fundamental perspective. So we have taken this intrinsic dimension, which is a metric for the complexity of a data set. So what this means is basically the intrinsic dimension is the minimal amount of dimensions that you need to represent your data. So for example, imagine you have a feature vector that is 512, has 512 entries, so it has 512 dimensions, right? So, but most likely a lot of those dimensions aren't necessary, so to speak, and could be collapsed into others. And this intrinsic dimension is the amount of dimensions that you need to represent your data with as little dimensions as possible. I think maybe you are familiar with this complex concept from PCA analysis or something like this, where we also do this dimension reduction thing. And this estimation is just a value of this minimal value. So for this, we kind of wanted a metric to see how much harder it becomes for a neural network to understand this perturbed data set as compared to the one if we train it on original data, which is not perturbed. How much harder does it become for a neural network to understand the perturbed data? This is a little bit tricky because it's not that easy to evaluate this intrinsic dimension. So what we did here is we relied on some work, on some recent work to estimate this intrinsic dimension, and this basically uses the fact which is often described as the curse of the dimensionality. So the larger your data set becomes in dimensions, the farther your data becomes spread out, right? The more dimensions you have, the more harder it becomes to separate the data, because the data points are very far from each other at some point before dimensions are introduced. And by taking nearest neighbor estimates, so basically calculating the average distance between feature representations of the entire data set, a pairwise nearest neighbor thing, we can basically estimate with some mathematical formulas, we can estimate this intrinsic dimension from this calculation. What we do here is basically we have this manifold of data, or in this case, feature vectors from different layers of a neural network. And we do this 2NN, so two nearest neighbor estimator, and we calculate these distances here between those representations in the space of the latest representation. Okay. And yeah, so as I already mentioned, we have taken a baseline without the additional noise. So this is the data as it came. And with this, we have trained the model to detect the individual people in the images. And yeah, what have we achieved here? We have a baseline, and maybe remember those numbers. So this is an AP at 0.5 IOU of roughly 92, and the other one, which is the interval-based one, of 41.4, right? So these are our baseline readings. And yeah, you can already see that those have become quite significantly smaller if we introduce the noise. right? So those are the values on the network trained with original data, but inference was done on the noise data. Oh no, excuse me. This is the signal to noise ratio. I'm ahead of myself. And yeah. So excuse me, I take that back. So we have here the signal to noise ratio, and here we have a comparison of the denoising techniques that we have used. And the higher the signal to noise ratio is, the better. So we already see that we have a loss here, of course, in the disturbed ones, but we can recover some of it with our denoising techniques. And we see that, for example, our wavelet filter and the bilateral filter do particularly well in the signal to noise ratio, which we kind of expected because those are the more complex and more sophisticated techniques. Yeah. Exactly, and here we come to those to the average precision values, and here we have a comparison of all of those different noise levels. So the error bars, the bars here give us an overview of the performance across all of those noise modalities that I just showed. And with the this line indicates the mean performance, and the dotted line is the median performance of that denoising. Yeah, and we see here that our the lower we get here is the better, right? Because this axis is inverted, so the lower we get here, the better. And we see here that the wavelet filter, it produced almost the best values. It didn't quite produce the best values because, funnily enough, the mean filter also did quite well. But if you see, if you look at the error bars, the variance of the performance of that filter was higher than the wavelet. So yeah, we see a similar performance, a similar phenomena occurring at the medium noise level. Here we also have the wavelet filter that is came out ahead of the others, and also here on the high noise level. So we can recover quite a lot of lost performance with the wavelet filter. Yeah, that was a mixture of the noises here that we applied with low, high, and medium noise levels. And here we get to the interesting part. This is the where we have calculated this intrinsic dimension of the data set at different layers of the data of the network. So we went progressively ahead and have taken the features calculated at this layer depth and have, with those representations, calculated this intrinsic dimension. And we can see here that that the wavelet filter and the bilateral filter produce the lowest intrinsic dimension, which is the best for us because, remember, the lower the dimension, the better our theoretical capability of classifying things, the less complicated the data set is. And if we look back to the original one, we are about, for example, at layer 4, we are roughly at 15. And yeah, roughly at 15, and we could recover a lot of that performance in this intrinsic dimension of the data set with this filtering approach. Yeah, this is a little bit more of that compared to average precision, I think. So yeah, then just let me come to a conclusion. We have, obviously, we didn't need to prove it. We already knew that that the low level noise would have minimal impact on the performance quality, and progressively with introducing more noise, it would become worse. Of course, we need this. but we also could show that with classical methods of denoising that don't require any pre-training, that do not require many parameters, hyperparameters to tune, we could significantly improve our detection quality. And the wavelet filter has proven the best, the most versatile of all those techniques. It's also a technique that is available out of the box in most Python packages, so you don't need to do a lot to make this run on your data. And yeah, basically using this for denoising has improved our results quite a bit. So yeah, thank you. That was my presentation on this this recent work that we have done. Do you have any questions for me? Maybe we can discuss this a little bit.
So what is the main reason of noise? Is it light or?
It's very there's various sources of noises. For example, first of all, this wireless transmission that I have mentioned at the beginning, because with the agricultural machines, with their size that they have, especially those harvesters, a lot of companies rely on this wireless transmission. This introduces a lot of noise because it is sometimes also still analog. Then we have obviously, for example, dust. That is a very big reason, because those machines produce a lot, especially in the summer when they drive and harvest. The soil is dry, and thus it's very prone to producing the dust. And there's also other forms. For example, remember salt and pepper noise. If your sensor itself is damaged, which happens maybe sometimes even straight out of the factory, or with the lifetime of the sensor, some pixels just die. And there's also things like other environmental factors, like, for example, rain, you could describe as a source of noise, or also these blooming artifacts that we saw. Yeah.
How could we know which type of denoising filter to plant?
Yeah, so by choosing a lot of different noise models, because the charts that I showed you have been taken across many noise modalities, right? So we have the Gaussian noise in there, salt and pepper noise, and all the others, and Brownian and whatever. And across all of those noise modalities, the wavelet one has proven to be the most versatile. So you can also, if the mean filter also hasn't done that badly. This is, of course, the simplest filter that we can imagine. So maybe if you want to start with that, you could, but also the variance of its performance is a little bit, different. And so we think that the wavelet one is the best choice, because it offers a very good performance across many of those image noise modalities. Inference time. So specifically, we wanted to look at this inference time, and you're right. I think maybe that's your second question that you might have. Why didn't we just train with noise data? It's mostly because we wanted to look at this intrinsic dimension of those things, and how this would affect the complexity of the data set. But you're of course right. Maybe the best solution would be to train on noise data. This is also a very common technique of data augmentation, where you just force the network to ignore those kinds of noises. And I think for the best examples, you would couple this, right? So you would robustify your network at the training stage, and then on the inference stage, also use those kinds of techniques to remove anything that might be bad or disturbed.
So, what sort of sensors do you feel producing more noise?
There's noise in every single sensor that we use, especially for the perception types of perceiving the environment, right? So the main sensors that we use, we saw that already in the presentation from Professor Burns. It's cameras. Those cameras introduce noise, as I mentioned, through transmission error, through sensor pixel failures and whatnot. But there's also LiDAR, right? And LiDAR, if you remember, it's based on reflectivity. So if there is something in the air, it will recognize that as something that is there. We have huge problems with that. For example, on the Unimog machine, we trained our proving ground, our testing facility was at garbage dump, so to speak, or a construction debris dump. And this always used to become very dry and also very dusty in the air. And then it literally, you could see the dust clouds in the LiDAR view also, because, and then basically it's hard for us to filter out semantically if this is a real obstacle or if that's not a real obstacle. So this denoising takes away a lot of that work, because otherwise we would have to cross-correlate the LiDAR with the camera view and see if this is semantically feasible, if the one shows an obstacle but the other one doesn't, and that just introduces a lot of complexity. And finally, we have sonar also we use a lot, and this is, of course, if you think about flooded areas, there's a lot of debris in the water that isn't necessarily, can't be necessarily regarded as an obstacle, maybe like sticks, leaves, whatnot. And also you have a lot of echoing effects, right? So there's a lot of things where the sound wave can get reflected, and sometimes it gets reflected twice, or even there's very complex effects with that also introduce a kind of noise into that scenario. So we encounter those things at every level, basically. One look at.
One more question. So do you use the multispectral sensors, and for what sort of data?
We also have multispectral sensors, and we have started with this rather recently. We are using them also on drones. Yeah.
For prop sensors?
Yeah, I think we will have a talk later also when I don't know if my colleague will show that, but for example, in Germany, we have those wine yards that are on the steep slopes. And for example, for those, we have concluded the NDVI stuff. And maybe that will come also in the next.
Have you implemented any sort of denoising filters at the hardware level, or it is recommended to use it at the software side?
It's actually a very good idea, because I could very much imagine that being implemented in FPGA, for example, or something like that. We also have colleagues who deal with FPGAs, but we haven't done this yet. But this is a very good idea.
So, one last question. As a layman, so when you are talking about noising, denoising, it means you're talking about the pixels. Right?
Exactly.
So when we have a picture of then prop, so how these models replaced as noise pixel with the original ones are, how they denoise?
There's different ones. Maybe I go back here a little bit.
Do they put some average values there? Or?
Yeah, we have, for example, we have this mean filter that does exactly what you just described. The median filter does the same with the median value. Gaussian blur is basically does the same, but with a weighted fashion. So you have a window which you slide over the image, and in this window you calculate a weighted average. And this wavelet filter in particular, this one is interesting because it's frequency based, right? So you have these. Unfortunately, I don't have the slide for this, but basically, if you're familiar with the Fourier transform, that takes your image and divides it into frequencies, right? And then you can go ahead and say or make the assumption that the noise that is in your image is very high frequency, right? Because this noise, it's like one pixel, it has a very high peak and then nothing next to it, which is opposite to normal data, which is more continuously and isn't regarded as high frequency. And once we have this frequency frequency-based decomposition. We can divide our image into frequencies. Then we can just say we cut off at a certain frequency, right? So we don't, everything that is higher than a certain frequency, we just throw away. And then what is left, we combine back together into an image. And this image will then contain the semantical information that was there, because this is contained in the low frequency band, but the noise won't be there anymore because it is, was thrown away in the frequency step. Okay, then, thanks a lot for your attention.